Hello friends, heartily welcome to this second video based on chemical kinetics. In this video, we will study the rate law or rate expression. So we will begin from the factors affecting rate of reaction. There are certain factors on which rate of a chemical reaction is depends on. See, first of all, how the rate of a chemical reaction is depends on concentration of reactants. So rate of any reaction except than that of the zero order is directly proportional to the concentration of the reactants. It means more is the concentration of reactants, greater is the rate. And that's why the rate of any reaction is greatest in the beginning and it goes on decreasing as time passes, because we know that at the beginning the concentration of the reactants is very high, and that's why rate also very high. Then second factor, temperature. Rate of any chemical reaction is again directly proportional to the temperature. In this case, 10-degree rise in temperature increases the rate 2 times or sometimes 3 times. That is what. Pressure. For the reactions involving gases, rate of reaction is also directly proportional to the pressure. Fourth one, presence of catalyst. Positive catalyst increases the rate of reaction and negative catalyst decreases the rate of reaction. So there are certain catalysts, in the presence of them the reaction rate increases. Presence of light. There are some reactions which occurs only in presence of light. Such reactions are called photochemical reactions. In such reactions, rate of reaction is again directly proportional to the intensity of light used. And last, surface area of the reactant. Rate of reaction again directly proportional to the surface area of reactant. As the surface area increases, then the rate of reaction is also increases. Now see, let us study the rate of reaction and reactant concentration. Rate law or rate expression. So in first video, we have already studied the rate equation. So that rate equation that is related to the rate of a reaction with the coefficients of the molar concentrations of the species, and we have seen that the coefficients of the species are used to divide the corresponding species. The rate law or rate expression is different than that of the rate equation. The rate of a reaction at a given temperature for a given time instant depends on the concentration of the reactants. Such rate concentration relation is the rate law. See, in this case, the how the rate of a reaction at given temperature for a given time instant depends on the concentration of the reactants. How it is related to the concentration of the reactant is given by the rate law or rate expression. See, what is the rate law? It is defined as an experimentally determined equation that expresses the rate of a chemical reaction in terms of molar concentrations of the reactants that raised to the power. See, so rate law or rate expression It is very important to note that. So this is the experimentally determined equation, or it is defined as an experimentally determined equation that expresses the rate of a chemical reaction in terms of molar concentrations of the reactants that raised to the powers. So that is in the form of their exponents. How the rate is depends on the exponents or the powers of the molar concentrations. So that is given in the rate law or rate expression. Let us see the explanation. Consider general reaction. AA plus BB gives CC plus DD. The rate of a reaction at given time is proportional to its molar concentrations at that time raised to simple powers. So for such a general reaction, the rate is depends upon the, or it is proportional to the molar concentrations of the reactants, the raised to their simple powers. So that is what. How the rate is depends upon the exponents or the powers of the molar concentrations. So the rate law or rate expression gives the relationship between the rate of reaction and the molar concentrations with their exponents. See here, mathematically we can write this. Rate of reaction is directly proportional to molar concentration of A to its power x into molar concentration of B raised to the power y. Or simply this can be written like this: rate is equal to K molar concentration of A x into molar concentration of B raised to y. So where the x and y are the exponents or powers. पहा, ज्यांना आपण घातांक म्हणतो. तर अशा पद्धतीनं मोलार कॉन्सन्ट्रेशनचे जे घातांक आहेत त्यांच्यावरती रेट ऑफ रिॲक्शन कसा डिपेंड असतो हे रेट लॉ किंवा रेट एक्सप्रेशन आपल्याला सांगते. आणि महत्त्वाची गोष्ट ही टोटली एक्सपेरिमेंटली डिटरमाइन्ड गोष्ट आहे. पहा, where K is the proportionality constant is called the rate constant, which is independent of concentrations and varies with temperature. So again the value of K, that is called as the proportionality constant, and it is independent upon the molar concentrations, but it depends upon the temperature. It varies with temperature, it changes with temperature. The above equation indicates the dependence of the reaction rate on the concentration of each reactant. The above equation indicates the dependence of the reaction rate on the concentration of the each reactant. This equation is called as differential rate law or simply rate law. So that is what, how rate is related to the molar concentrations that raised to their powers. So this equation is also called as differential rate law or simply the rate law equation. The powers, that is exponents x and y of the concentration terms A and B in the rate law not necessarily equal to the stoichiometric coefficients, that is A and B appearing in the general reaction. So what is that? In this case, the x and y of the concentration terms A and B in the rate law not necessarily, they may be sometimes equal to the coefficients A and B or may not be equal to. So it is not necessary equal to the stoichiometric coefficients. पहा, आपण जनरल रिॲक्शन मध्ये पाहिलं, रेट इक्वेशन लिहित असताना हे जे कोएफिशियंट्स आहेत आपण ते डिनॉमिनेटरला घेतले किंवा त्या करस्पॉन्डिंग स्पेसिसला या कोएफिशियंटनी आपण डिव्हाइड केलं. परंतु रेट लॉ किंवा रेट एक्सप्रेशन लिहित असताना लक्षात घ्यायचं आहे आपल्याला. सो द रेट of a reaction, how depends on the concentrations or the molar concentrations of the reactants and the power raised to power, that is the corresponding exponents. So these exponents may or may not be equal to the coefficients. Need not to, they have the same values as that of the coefficients. Thus, it is important to note that the x and y are experimentally determined. So this is very important. So the values of x and y, these exponents, are obtained by performing the experiments, by studying that specific reactions. How the rate is depends upon the molar concentrations of the specific reactants, that is checked or tested by performing the experiments, by performing that reaction repeatedly. So in this way, so this is a completely experimental thing, and x and y may be simple whole numbers, they may be zero or fraction. x आणि y जे एक्सपोनंट्स आहेत त्यांच्या किमती होल नंबर्समध्ये असू शकतात, झिरो सुद्धा असू शकते किंवा फ्रॅक्शनमध्ये असू शकतात. लेट अस सी द सर्टन एक्झाम्पल्स. फॉर एक्झाम्पल पहा, इफ एक्स इज इक्वल टू वाय इज इक्वल टू 1, रेट लॉ, दॅट इज रेट इज रिटन लाईक दिस. आता एक्स आणि वाय ची किंमत जर 1 असेल तर पहा, दॅट इज ॲट युनिटी. रेट इज इक्वल टू व्हॉट? सी, K molar concentration of A into molar concentration of B. So if the value of x and y is equal to 1, so at that time the rate is depends upon what? Now see, that is linearly proportional to the molar concentrations of these reactants, like this. Or in this case, as the molar concentrations of A and B, now see, they are at unity. They are at unity. So that's why the rate is equal to the K, that is the proportionality constant. See here, so this is called as the rate constant. This is called as the rate constant. What we have to note? When the molar concentrations of the reactants are at unity, at that time, that is rate is equal to K. That is rate is depends upon the value of K, or that is depends upon the rate constant. So that is the rate constant. The equation implies that the rate of a reaction depends linearly on concentrations of A and B. If either of concentration of A or B is doubled, the rate would be doubled. So as the rate is linearly proportional to the molar concentration of A and B, and that's why in such reactions, either A or B, any one of the reactant is doubled, then what happens? The rate would be doubled. The rate increases and it would be doubled in such cases. Let us see the second example. For example, x is equal to 2 and y is equal to 1, then rate is written like this. See here, rate is equal to what? K molar concentration of A, its power, it raised to power 2 into molar concentration of B, as the value of x is 2. If concentration of A is doubled, what it indicates? If concentration of A is doubled, keeping that of B constant, the rate of reaction will increases by a factor of 4. So this is very important. Now see. So in this case, what is the meaning of this? एक्सपोनंट्स किंवा हे जे घातांक आहेत यांच्यावरती रेट कसा डिपेंड आहे पहा. रेट इक्वेशनमध्ये या ठिकाणी एक्सची किंमत जर 2 असेल, सो मोलार कॉन्सन्ट्रेशन ऑफ ए रेज टू पॉवर 2, at that time what happens? How the rate is depends upon, see now, on this reactant. If concentration of A is doubled, keeping that of the B constant, the rate of reaction will increases by a factor of 4 times. चा स्क्वेअर असल्यामुळं, एक्सपोनंट 2 असल्यामुळं आता या ठिकाणी काय होतं पहा, याचं जर कॉन्सन्ट्रेशन आपण डबल केलं, याचं कॉन्सन्ट्रेशन डबल केलं तर याचा स्क्वेअर असल्यामुळं ॲक्च्युअल रेट ऑफ रिॲक्शन काय होतो, 4 टाइम्सनी वाढतो. दॅट इज वॉट, दिस इज इम्पॉर्टंट. अगेन, इफ x इज इक्वल टू 0, the rate is independent of concentration of A. पहा, या ए स्पेसिसच्या मोलार कॉन्सन्ट्रेशन जे आहे त्याचा एक्सपोनंट जर 0 असेल, व्हॉट इट इंडिकेट्स, द रेट इज इंडिपेंडंट ऑन द कॉन्सन्ट्रेशन ऑफ दिस ए. थर्ड एक्झाम्पल, सिमिलरली, if x is less than 0, if the value of this exponent x is less than 0, the rate decreases as a increases. त्याचा अर्थ असा होतो की रेट डिक्रीज होईल जर याची व्हॅल्यू आपण वाढवली तर. अशा पद्धतीनं हाऊ अफेक्ट्स द व्हॅल्यू ऑफ एक्स. सो दिस इज इम्पॉर्टंट. देन let us study how to write the rate law. So again, this is very simple. Once you understand the rate law or rate expression, how it can be written. Here, consider the reaction 2H2O2. So that is the decomposition of hydrogen peroxide. It gives water and gaseous oxygen. If the rate of the reaction is proportional to the concentration of H2O2, the rate law is given by. See, we don't know. So what is the rate of this reaction? So experimentally or practically it is observed that the rate of such reaction is depends on or directly proportional to the concentration of the hydrogen peroxide. So this is experimentally tested or checked or determined. So it is observed that when the concentration of H2O2 is increased, the rate of the reaction increases, and that's why, as it is directly proportional to the concentration of H2O2. So this is practically checked. From that, now we can write the rate equation for this like this. Rate is equal to what? K, molar concentration of H2O2. So again, if the concentration is doubled, the rate is get doubled. When the concentration is doubled, the rate is get also doubled. How? The rate is depends upon this. So that is shown with the help of rate law or rate equation, or that is the rate expression. For the reaction, see here, NO2 gaseous plus CO gaseous gives NO gaseous, CO2 gaseous. The rate of reaction is experimentally found to be proportional to the square of the concentration of NO2 and independent that of CO. So therefore we can write now. So this is experimentally observed. What? That is, rate is directly proportional to the square root of concentration of NO2 and independent that of the CO. So that's why this can be written like this. Rate equation or rate law or rate expression for this can be written in the form of exponents like this. Rate is equal to K, molar concentration of NO2, its square, that is power raised to 2, as rate depends upon this square of the concentration of NO2, and the concentration of CO, that is molar concentration of CO raised to power 0, as rate is does not depends upon this, so that it is need not to write that. So we can write for this the rate expression like this. Rate depends upon this only. Okay, then let us, we will solve the few numericals based on this rate law or rate expression. See, the first numerical, write the rate law for the reaction A plus B gives P from the following data. So here data is given. From that we have to write what? The rate law for this general equation. अशा पद्धतीनं आपल्याला हे डाटा दिलेला आहे, माहिती दिलेली आहे. पहा, फर्स्ट, सेकंड, थर्ड इनिशियल कॉन्सन्ट्रेशन्स दिलेले आहेत ए चे, बी चे, आणि इनिशियल रेट दिलेला आहे रिॲक्शनचा. पहा, अशा पद्धतीनं 3 आपल्याला वेगवेगळ्या यांच्या व्हॅल्यूज दिलेल्या आहेत, मोलार कॉन्सन्ट्रेशन्स दिलेले आहेत. हाऊ टू सॉल्व दिस न्यूमेरिकल? We have to write the rate law. for this reaction now with the help of this data provided. See here now how to solve this solution. Suppose that the rate law is rate is equal to K molar concentration of A raised to power X into molar concentration of B raised to power Y. To write the rate law, the values of the exponents X and Y are to be calculated. So I have to calculate now the values of X and Y in order to write the rate law. So how this can be done? See here, from the above observations, first and second, see here, first and second, see here, first, or we can write this is also R1 is equal to, now see this is the rate, now see this is the rate, so rate, so this is equal to what? Molar concentration of A, molar concentration of B raised to the powers X and Y. Then second, see, so again this is the, we can say R2 or second rate, rate is given, rate is given here, and these are the concentrations, concentration second. So once by using this first and second uh, observation, we can write, see here, divide first by second, divide first by second, dividing second by 1, see here, we will get like this, second, that is R2 upon R1, R2 upon R1, like this. So this is very simple. So these are the rates, these are the concentrations, R2 upon R1. So by calculating this, we will get the answer 1.5. Power is same, 1.5 here. Look at this, 1.5. And here, see here, 0.6 divided by 0.4 molar concentrations of A, molar concentrations of B, like this. So this is equal to, see here, so this is get cancelled, 0.6 upon 0.4 X, like this. See, so 1.5, this is again equal to, answer of this is also 1.5 X. So by dividing this 1.5 to this, we will get the value of X, hence X is equal to 1. See, so from observations first and third again, which are given in the table, separately the rate law gives, पहा rates दिलेले आहेत, कॉन्सन्ट्रेशन्स दिलेले आहेत, आपण R3 म्हणूयात रेट आणि हे कॉन्सन्ट्रेशन्स. आता या ठिकाणी x ची व्हॅल्यू जी आहे 1 आपण काढलेली आहे, म्हणून एक्सपोनंट x इथे घेतलेला नाही आहे, सिन्स x इज इक्वल टू 1. y आपल्याला डिटरमाइन करायचा आहे. देन फोर्थ, see here, so that is again in this case the dividing fourth by third, we write pa like this, fourth by third. So by calculating this, see here, rates, these are the concentrations, we will get now, see what is that. So value, answer of this is 8, and again here the answer of this, that is, see here, 8 is equal to this 2, answer of this is 2, and 0.6 upon 0.4 y here. So therefore now, so 8 divided by 2, we can write 4 is equal to 2y again, therefore we will get y is equal to what? 2. So in this way the values of x and y can be determined. The rate law is then written like this, rate is equal to what? Proportionality constant K, molar concentration of A, as the value of x is 1, need not to write here. So molar concentration of B raised to the power 2. So in this way the rate is depends upon the square of the molar concentration of the B, or that is the rate equation or rate law or rate expression can be written for this. Then at last see one more numerical. Second problem. For the reaction 2, look at this reaction. 2NOBr gives 2NO2 plus Br2. The rate law is given there. Rate is equal to this. Look at that. The rate of the reaction is directly proportional to the square root of NOBr. Square of the this. If the rate of the reaction is, rate is given, moles per liter per time. When concentration of NOBr is like this, concentration also given NOBr like this. See here. What would be the rate constant for the reaction? So we have to determine or calculate the rate constant. So there may be the such type of numerical in which we have to calculate the rate constant. So simple, see here. So rate is given by this expression. We have to calculate now K. The rate is given. The concentration is also given this. So we can write now, see, K is equal to rate upon this. So just substituting the values, we will get, by substituting the values, we will get like this. So that is equal to what? This. Okay. So in this way, the rate law is applicable. So what we have studied in this video, that is the factors affecting the rate of reaction, then rate law or rate expression, and how to write this rate law or rate expression, and how to solve the numericals which are based on this. So I think this is enough. So we stop here. So don't forget to like and subscribe the video in order to watch the incoming videos. So thank you.